And now a few more definitions about sets. Two definitions that you probably remember from previous math classes. If A and B are sets, then this symbol is the union of A and B. The union of two sets, it's defined to be the set of all x such that x is either in A or x is in B. And in English, what this or means really is either one or both. So A union B is a set of all the elements that are in either one of them or in both of them. So the union of two sets tends to be a bigger set than either of the two original sets in most cases. The intersection of two sets is a set of all x such that x is in A and simultaneously x is in B. It's each element that sits in both sets. So that tends to be a smaller set. You can have two large sets and their intersection is only the elements that they have in common, the elements that are in both sets. So this one is union and this one is intersection. The intersection symbol is just the upside down union symbol. All right, and the key words, union, think of or. That's why it's a bigger set. You list all of the elements that are either in this set or that set, either in set A or in set B, where this one is more restrictive. Intersection requires that each element has to be in A and also it has to be in B. Elements that they share in common. So if we took a couple of simple short examples here. If the set capital X is 1, 2, red, not all the elements have to be related to each other in a set. We have two numbers and a color. And Y is equal to 3 and blue. We have two sets. Let's figure out what X union Y is and X intersect Y. Well, the union is a set of all elements that are either in X or Y. So we have 1, 2, 3, red, and blue. Remember, order doesn't matter. I chose to put the numbers first, 1, 2, 3, and then the two colors. Didn't have to do that though. This said it's the same as if I said red, 1, 3, 2, blue. And what's the intersection? What is the set of all x such that x is in this set and also it's in this set? Well, notice they share no common elements. The intersection happens to be, in this case, the empty set. You don't have to write both of them. You can write either one of those to represent the empty set. And by the way, in case I don't mention this later, there's a word for two sets that don't have any elements in their intersection. It's called disjoint. And I think I'll talk about that later, so I'll just mention it now. X and Y are disjoint sets because their intersection is the empty set. Let's look at a couple of larger examples. Oops. Let's take the set of integers unioned with the natural numbers. So I want the set of all elements that are either in this set or in this set. And if you think about it for a minute, that just gives you the integers. Is there a single number in this set that's not in the integers? No, there's not. This happens anytime one of the sets is a subset of the other. Natural numbers is a subset of the integers. And let's look at Z, the integers intersected with the integers. I need the set of all elements that are in this and in this. Every element in the intersection has to be in both of these sets. So I think, again, if you think about it for a minute, you'll come up with that. Again, that's because the natural numbers are a subset of the integers. And we could do the reals unioned with the integers. That's going to give us just the reals. The integers are already in the reals, so we didn't get anything new there. And the intersection of the reals with the integers, well, that's just going to be integers. So again, those are some special cases where one of the sets was a subset of the other. Now I think I'm going to try to put a theorem 0.2 right here. Hopefully that's in the view of the camera. Let's let A, B, and C be sets. I'm going to write down about 6 dozen or so properties that are always true about sets. The first one says that A intersect B is equal to B intersect A. You could call that the commutative property for the intersection of sets. If you're intersecting two sets, it doesn't matter which one you write first. This set is the set of elements that are in both A and B. This set is the set of all elements that are in both B and A. Same thing. The second one, A union B, is equal to B union A. On the left, you have the set of all elements that are in either A or B. On the right, you have the set of all elements that are in either B or A. That's exactly the same thing. The third one will look like something you've seen before. It is A intersect B intersect C with parentheses around the A intersect B is equal to A intersect B intersect C. That would be called the associative property for sets, for the union of sets. And IV, or number 4, we're going to have the same thing for intersection. Sorry, I hope I said that right. That's the intersection. We're going to have the same thing now for union. So it doesn't matter if you're taking the union of a bunch of sets. It could be more than 3. Order just doesn't matter. In fact, if I'm writing down the union of 3 sets, I don't use any parentheses at all. I would just write A union B union C. And same for intersection. A intersect B intersect C. You're intersecting 3 sets together. Order does not matter. And it can be 4 sets or 5 sets and so on. The fifth one, A intersect B union C. This one's the first one that may not quite be intuitive. It's going to look like the distributive property. I need to distribute the A to the B and the A to the C. So I'm going to take A intersect B union with A intersect C. Make sure you use parentheses. If you've got an expression with unions and intersections, it might look ambiguous. Make sure you put the parentheses in to make it perfectly clear. Then there's another distributive with A union B intersection C. And just by looking at the fifth one, you can probably figure out what the sixth one is. It's like a distributive property again. It's going to be A union B intersect A union C. And that is theorem 0.2. And I believe I'll pick 1 or 2 of those and prove them.